An object from another star system, 3I/Atlas, enters the solar system, streaking toward Mars with a speed and composition unlike anything seen before. Astronomers are shocked. It carries a carbon dioxide-rich payload nearly 8 times its water content, approaching Mars at 30 million kilometers while Earth is blinded by the sun. At the same time, NASA's Mars rovers report potential biosignatures in Jezero crater's ancient riverbeds. Is this just cosmic coincidence, a natural delivery of exotic ices, or something engineered with intent? This is what 3I/Atlas is really doing near Mars, and what happens next could rewrite the story of both Mars and interstellar science. 3I/Atlas is not just another comet. Its path through the solar system is hyperbolic, with an eccentricity greater than 1, a mathematical stamp that it comes from beyond our sun's reach. Astronomers confirmed this within hours of its discovery on July 1, 2025, as the object's orbit calculations showed it would never return. Instead of looping around the sun like a planet or most comets, 3I/Atlas is on a one-way journey, passing through at nearly 68 kilometers per second. That's about 150,000 miles per hour, far faster than any object born in the solar system. Its closest approach to Earth will be 1.8 astronomical units, or about 269 million kilometers, in December 2025. But even at that distance, it draws attention for another reason: the glowing cloud, or coma, that surrounds its icy core. When sunlight heats a comet, frozen gases and dust erupt outward, forming this coma and sometimes a tail. Most comets are dominated by water vapor, what astronomers call the dirty snowball model. But early spectra from 3I/Atlas show a different recipe, one where carbon dioxide is far more abundant than water. This is not what scientists expect from a typical comet. The classic model, shaped by decades of observations, says water ice should be the main ingredient, with smaller amounts of carbon dioxide and other gases mixed in. Here, the balance is flipped. The coma's composition hints at an origin in a much colder, more distant environment than our own solar system can provide. As 3I/Atlas races inward, its behavior is forcing astronomers to revisit the basics of comet chemistry and dynamics. The combination of speed, trajectory, and unusual coma signals that this is a true interstellar visitor, one that carries the secrets of another star system, and perhaps a different kind of cosmic history. Mars holds onto its secrets in the sediments of Jezero crater. Billions of years ago, a river carved its way across the Martian surface, spreading out into a broad delta. Here, layers of silt and clay settled, locking away traces of whatever life or chemistry once touched this ancient waterway. Among the patterns left behind, scientists have zeroed in on something strange: rounded, mottled patches scattered across the delta, known as leopard spot textures. These features have sparked intense discussion since their first high-resolution images, with some researchers suggesting they might be biosignatures, physical signs that life once flourished on Mars. Dr. Hiroshi Tanaka, a planetary chemist who has spent years studying Martian sediments, cautions against jumping to conclusions. He points out that, on Earth, river deltas are nature's vaults for organic molecules. Their fine-grained sediments protect fragile compounds from the harsh environment above. Mars, with its thin air and constant radiation, offers few places as promising for preserving ancient organics as Jezero's delta. But not every odd pattern is a sign of life. Dr. Tanaka's team has shown that similar spots can form through chemical reactions, mineral growth, or even the slow weathering of rocks over time. The challenge for Mars science is separating what belongs to the planet from what might have arrived from elsewhere. A delta like Jezero's is a perfect trap, catching organics whether they formed in Martian lakes or drifted in on dust and ice from space. As new claims about biosignatures circulate, the risk of confusion grows. The timing of 3I/Atlas's pass near Mars only sharpens the question. If a surge of new organics appears in the delta, is it a message from Mars's past, or a fresh delivery from the cosmos? The answers lie buried in the layers, waiting for careful science to reveal them. A comet's chemistry usually reveals its birthplace. For decades, astronomers have measured the balance of water vapor and carbon dioxide in comet comas, using these ratios to map where ice is condensed billions of years ago. But with 3i Atlas, the numbers do not fit any familiar pattern. On July 18, 2025, the Gran Telescopio Canarias recorded a carbon dioxide to water ratio near 8:1, an outlier by any standard. Most comets, even those from the frigid outer reaches of our own solar system, carry more water than carbon dioxide. Here, the script is reversed. The debate started as soon as the data hit the preprint servers. Some teams raised the possibility of a calibration artifact. Earth's own atmosphere is thick with carbon dioxide, and subtracting those bands from a faint interstellar target is notoriously tricky. But follow-up spectra from Keck and Nordic Optical Telescope backed up the anomaly. Even the lowest estimates, around 5:1, remain far outside the norm. The question now is whether this is a window into formation in a different kind of molecular cloud or evidence of radical processing by cosmic radiation during its long journey. Adding to the puzzle, astronomers noticed a green tint in the coma's spectrum. This glow is linked to molecules like dicarbon and cyanide, compounds that can shine brightly when driven by energetic chemistry. In 3i/Atlas, their intensity appears unusually high, possibly fueled by the same carbon dioxide-rich outgassing that sets it apart. Some researchers suggest this could mean the comet formed beyond the traditional water-ice line in a region where carbon dioxide freezes out first. Others point to selective sublimation or even the effects of radiation breaking down complex ices and releasing rare molecules. With each new observation, the chemical story grows stranger, and the clock is ticking for Mars-based instruments to capture a clear signal before the object slips away. The countdown to October 3rd has become a race against time. On that day, 3i/Atlas will sweep past Mars at a distance of just 0.19 astronomical units, about 28 million kilometers. In cosmic terms, that's a hair's breadth, especially for an object that began its journey in another star system. But the moment of closest approach brings a complication. Mars and 3i/Atlas will be almost directly behind the Sun from Earth's perspective. For weeks on either side of the flyby, sunlight will swamp the line of sight, forcing ground-based telescopes to shut their domes and wait. This solar conjunction, stretching from late September through late October, creates a blackout window. Earth's most powerful observatories, Keck, VLT, JWST, won't be able to track the comet or the Martian sky. Even radio links to Mars orbiters become unreliable, as solar noise drowns out signals. The timing is unforgiving. The flyby's geometry means that the best chance to observe any interaction between 3i/Atlas and Mars falls squarely within this period of scientific darkness. Missed opportunities like this are rare. The odds of an interstellar object passing this close to Mars during a conjunction are slim, roughly 1 in 100 per year, based on current models of interstellar traffic and planetary alignments. For planetary scientists, it feels like a cosmic dare, the most interesting visitor in decades, perfectly timed to slip past the only planet in the solar system with an active biosignature hunt, while the main audience is forced to look away. As the blackout approaches, attention shifts to the few eyes that remain open. Mars orbiters, running on pre-programmed routines, will be the only platforms able to capture data during the flyby. The pressure is on to maximize every observation window before conjunction cuts off communication. Every minute counts, and every dataset could be the one that breaks open the mystery. The clock is ticking, and the universe isn't waiting for anyone. Mars orbiters have become the last line of observation as 3i/Atlas sweeps past the red planet. Among them, ESA's Mars Express and the ExoMars Trace Gas Orbiter are now tasked with capturing whatever evidence they can before the window closes. Dr. Colin Frank Wilson, a project scientist for Mars Express, has described the effort as a rare scientific gamble, one that may never come again in this decade. The high-resolution stereo camera, or HRSC, aboard Mars Express is designed for mapping the Martian surface in striking detail. Its color channels span from 380 to 1,000 nanometers, but at a distance of 28 million kilometers, even this powerful instrument will see 3i/Atlas as little more than a faint dot. The projected resolution, about 128,000 kilometers per pixel, means the comet's coma and nucleus will blur into a single point. Only if the comet erupts with an unexpectedly bright outburst could HRSC hint at its true shape or size. The odds are slim, but not zero. On the trace gas orbiter, the NOMAD spectrometer offers a different approach. Its ultraviolet and infrared channels are tuned to detect gases like carbon dioxide and water vapor, the very compounds that set 3I/Atlas apart. In theory, a strong enough outgassing event could leave a chemical fingerprint in NOMAD's data. The instrument's sensitivity, proven in tracking trace gases in the Martian atmosphere, can reach parts per billion for some species. But for a faint, distant target, the signal must rise above the background noise, a challenge at the edge of what the spectrometer can handle. Both orbiters face operational hurdles. During solar conjunction, communications with Earth are patchy or lost altogether. Instruments must run on pre-programmed scripts with no chance for last-minute adjustments. Data collected during this blackout may sit in onboard memory for weeks, risking loss if storage fills before downlink resumes. The comet's predicted brightness, hovering near magnitude 17 or 18, pushes the detectors to their limits. HRSC and KSSIS might capture a point source. OMEGA and SPICAM are even less likely to see anything but the faintest glow. Dr. Wilson and his colleagues have debated how best to use these precious observation slots. They know the odds. Unless 3I/Atlas surprises everyone with a dramatic outburst, the most likely outcome is a handful of upper limits, measurements that say only what could not be detected. But even these constraints matter. If a spike in carbon dioxide or an unexpected spectral line appears, it would set off a scramble to re-examine every frame. The search for something truly weird, an abrupt change in outgassing, an exotic molecule, a dust grain unlike any seen before, will come down to the sensitivity and luck of these orbiters. For now, the best plan is to watch, record, and be ready to interpret whatever the instruments can catch. The universe has handed Mars orbiters a unique assignment, and they are racing to meet it, no matter how faint the signal. Speculation around 3I/Atlas splits into three main possibilities. The first treats the comet's close pass by Mars as a rare but natural event. Interstellar object flux models suggest a body like this comes within 0.2 astronomical units of Mars once every 50 to 200 years. That puts the odds for any given year between 1 in 100 and 1 in 200, a long shot, but not outside the realm of chance. Most astronomers see this as a statistical blip, a reminder that randomness sometimes creates patterns we're tempted to read into. The second possibility borrows from old terraforming dreams. Could 3I/Atlas be a delivery system, intentionally steered to Mars? The comet's chemistry is intriguing. An 8:1 carbon dioxide to water ratio, a green glow hinting at energetic molecules, and a path that brushes past Mars just as biosignature claims are making headlines. For this scenario to hold, there would need to be evidence of guidance, a non-random jet, an artificial isotopic fingerprint, or a trajectory shift that can't be explained by gravity or natural outgassing. The orbit is hyperbolic, there's no sign of non-gravitational acceleration, and radio silence rules out obvious signals. Still, Mars orbiters are on alert for anything odd: a spike in rare isotopes, a sudden burst of gas, or dust grains with unfamiliar chemistry. The third lane is Panspermia, the idea that life's building blocks can hitch rides across the galaxy. If the comet's coma contains complex organics, or if isotopic ratios in its dust echo those in meteorites or ancient Martian rocks, it could support this theory. But proving panspermia is tough. Even a surge in organics during the flyby won't be enough. Scientists will look for isotopic fingerprints, ratios of carbon, nitrogen, and oxygen that don't match anything from Mars or the solar system. Only then could coincidence be ruled out. Each scenario sets its own bar for evidence. For now, the odds favor nature, but the search for something stranger continues. Rumors about 3I/Atlas have spread as quickly as the object itself, fueled by memes of cosmic clocks and claims of engineered delivery. But in science, Extraordinary stories demand extraordinary evidence. Yet, the origin of the high carbon dioxide content and any connection to Martian biosignature studies remain unresolved. The evidence so far does not support artificial intervention, but it deepens our understanding of interstellar chemistry and the challenges of interpreting planetary anomalies. What 3I/Atlas is doing near Mars is a rare natural experiment, one that will test our tools, our skepticism, and our ability to separate signal from noise in the search for life.